Okay, so I think you probably found your coffee, you found your Danish, and you found your way back to your seats. Okay, oh, there are my slides. So welcome back. Just a point of order, if you can please check to make sure your cell phones are off. That would be greatly appreciated for the final series of speakers and for the panel discussion. So, I had you do some homework over the break, and we'll try to probe that thinking that you did during the panel discussion. I first want to share a little bit of, again, some of the national activities that are happening coming out of AMP. Not too long ago, the President Obama, announced the creation in his 2013 budget, which depends on the vagaries of elections and budget cycles, but announced the creation of a national network of manufacturing institutes, which would be a network of innovation manufacturing institutes. There would be 15 of them around the country, is the idea, funded pretty significantly from the federal government with matching funds from the states and matching funds from industry, collaborations between industry and academia, really to create, and I'll slightly draw the analog if you're familiar with it, to the Fraunhofers in Germany, but trying to create an organization, a nonprofit organization that really tries to bridge the gap, cross the valley of death, impedance match between academia and industry, whatever metaphor you want to use. So whether or not this network is created, again, will depend, but in 2013, but in 2012, the pilot institute will be created. By the end of the year, there will be a pilot institute in manufacturing innovation. This pilot institute will be in additive manufacturing being very broadly defined as anything that is not subtractive manufacturing. Quite logical. And the actual call, the broad area announcement for this went out less than 3 weeks ago. I've been part of the MIT response. We're collaborating with a number of universities in the greater Northeast region to put together our vision for what this pilot institute may look like, and there will be a number of other teams around the country proposing this. But whether or not it comes to the greater Northeast region or Texas or California, wherever it may end up being, there will be a pilot institute in additive manufacturing. So it's actually a pretty exciting endeavor to try to really take some of these issues that we're understanding in terms of what's coming out of academia, what are the needs of industry, and creating an institute to address those issues. So that's at the national scale. And you can learn a lot more, easy to remember webpage, manufacturing.gov. So I want to talk to you a little bit about the Master of Engineering in Manufacturing program. I think when most of you were in school here, we did not have this degree. It's now a 7-year-old degree. It's a unique degree, and let me just bump through all of these here. The degree sits within the Department of Mechanical Engineering. It's a 1-year graduate degree, a comprehensive manufacturing curriculum. So manufacturing, the big M, everything from product design, manufacturing physics, manufacturing systems, and business. Uniquely, it's taken as a cohort. The students go through the program together. They all take the same 8 classes. In each of those classes, there is group effort, project effort as a significant component of it. They uniquely are introduced to a very systems perspective when they come in. So they have an engineering background. Most of them are mechanical engineers, but we have a spectrum from civil engineering, mechanical, electrical, and the full spectrum. But give them sort of the opportunity to use those tools in a manufacturing and group context, or doing real engineering in the industrial context, and introduce them to the systems. The capstone for what they do, their thesis, the thing that forms their thesis, is a group project in a company. So part of what I do is engage quite heavily with the manufacturing companies in the greater New England, Boston region to understand what are their immediate operational challenges. What are the potential opportunities to have 3 very bright, motivated graduate MIT students that understand manufacturing and the big picture of manufacturing to come in and for 8 months out of the 12 months that they're in the program to be engaged with the company, addressing a real bottom line impacting, in the line of fire initiative at the company. So we have this very strong industry connection. So the unique aspects, comparing to the MEng to the Master of Science. So it's non-research, comprehensive manufacturing curriculum, taken as a group, as a cohort, giving them the sort of engineering tools, practice, the systems, project-based, and very strong connection with industry. The pillars I think I outlined, but sort of manufacturing in the very broad sense, the big M, so manufacturing physics, manufacturing design, manufacturing systems, connection to the global enterprise of manufacturing. We have numerous outside of the classroom activities that augment and enhance what they see in the classroom, both the projects, seminars that we invite industry leaders to come in, everybody from the shop floor through the CEO level, and these group projects. And we've been doing this now for 7 years, 12 years if you include the time where we actually created the degree in Singapore as part of our Singapore-MIT Alliance collaboration. Doctari Diagnostics and Varian Semiconductor have been with the program, sort of a collaborative company, for a number of years. Just want to give you a brief example of the types of projects that our students will do. In this case, Doctari makes a microfluidic device for monitoring HIV, the CD4, the white blood cell count in blood. Our students have gone in and really helped them have the perspective of the mistake that they made when first outsourcing everything to Germany. So there's been, over the 3 years, a steady progression of re-importing the manufacturing expertise from offshore back into Cambridge. They're now manufacturing in Cambridge. Varian Semiconductor, which is now owned by Applied Materials, we've been engaged with them for about 5 years now, but addressing everything from new product introduction to factory floor redesigns for new product introduction, identifying waste within the manufacturing process. So just wanted to give you a flavor for the nature of the projects that these students will do within the context of the Master of Engineering and Manufacturing program. So when I asked before if you would encourage your children or your grandchildren to go into manufacturing, part of the reason that maybe you haven't done so, there haven't been good avenues by which they could gain the expertise in the academic environment to really understand and engage with industry afterwards. So we think that this is definitely a degree program that can help bridge that gap. So just wanted to introduce you to that as both a national initiative, the National Network of Manufacturing Institutes, and more close to home, the Master of Engineering and Manufacturing program. So with that, I'd like to introduce our next speaker. We have 2 more speakers, our alumni entrepreneurs. So first I'm going to introduce Marcy Black. Marcy's co-founded BandGap Engineering in 2007 here in the Boston area and is the inventor of the fundamental intellectual property. Today she's going to share with us how BandGap is commercializing silicon nanowire solar cells for low-cost photovoltaic electricity.
Hi, I'm Marcy Black, the founder and CTO of BandGap Engineering, but more importantly, I'm a class of '94 in course 6-1. So.
I also serve as AV.
So I thought I'd start by first explaining a little bit about what my company, BandGap Engineering, does, and then spend the majority of the time talking about the solar energy market in general, and in particular using it as a case study, since what's happening right now in solar cell manufacturing in the US is an extremely interesting and dynamic case that I'm convinced will be studied for many years to come. Oh, and then, I'm sorry, and then I want to conclude with a very un-MIT-like way. I'm going to present a problem instead of presenting a solution. And hopefully with the combined intellect in the room, maybe it can facilitate some discussions that will eventually lead to the solution of this problem. So BandGap was founded in 2007. We're a spin-out of Los Alamos National Laboratory, although a lot of the people at BandGap come from MIT. We're officially spun out of Los Alamos. And we're headquartered in Woburn, Massachusetts. And BandGap is working to commercialize silicon nanowire solar cells, or photovoltaics. And by using these silicon nanowires, we are working to make solar electricity cost competitive without subsidies compared to conventional energy sources. So we're venture-backed and pre-revenue. And I'm very proud of the very strong team we have, as well as our business model which works in the very difficult business environment of today. So it's MIT, so I thought I'd talk a little bit about the technology behind what we're doing. We have 3 different phases that we're bringing our technology to market. The first phase is one up there. It's the near-term strategy. So we're placing nanowires on top of a silicon wafer, and we're running that silicon wafer through existing equipment set lines. And by doing that, we get a boost in efficiency. And the higher the efficiency, the more light you can convert into electricity, and therefore the more power out of a cell that you put on your roof for the same area. So the reason why we get a higher efficiency is a couple reasons, but a large part of the reason is that the nanowires are smaller than the wavelength of light. So when the light comes in, it sees a composite material. It doesn't actually see the nanowires. And so the effective index of refraction is graded, meaning it slowly changes, and that leads to very low reflection. When you have less reflection, that leads to more light absorbed in the material, and more light absorbed means more electricity out. So we therefore get a higher efficiency from these cells. Compared to conventional cells, they usually use anti-reflection coating, which makes use of interference pattern in the material. And that only works at normal incident, so when it's in the middle of the summer at 12 o'clock noon. But when it's off the normal incident, the reflection goes up. Bandgap's technology has very low reflection at a wide variety of angles of incidence, so you also get more power at off-peak hours as well. So the nanowires also have another added benefit, that it traps the light better. So once the light gets into the silicon, it keeps it in better. And what that means is that effectively the silicon has more absorption for the same thickness. So we can get by with a thinner silicon than what you can do without nanowires. So our phase 2, which is in the midterm, that we're looking at is putting it on thin silicon solar. And ironically, when you go to thinner silicon, it doesn't become less fragile, it becomes flexible. And therefore, handling can actually be easier in this case. So that will decrease the cost of the material, it will increase the efficiency, and possibly it will help with what we call balance of systems cost, which is the cost of installing solar cells on your roof. In the long term, we're nano-engineering the silicon to produce higher efficiency solar cells by altering the band structure. So if you look, there's a schematic of our device, as well as a real picture of our shag carpet of nanowires that we place on top of a silicon wafer. Oh. Do you want to do it? Thank you. So I'm assuming, so that's all I'm going to talk about bandgap. If you want to talk more about bandgap, I'd be glad to talk to you afterwards. Also, our CEO, Rich Shablasky, is participating in his reunion from MIT as well, and so you can ask him questions. But I'd like to spend the rest of the time talking about the solar energy market in general. And I'm assuming with this well-educated audience, I don't need to explain why, if we want to sustain our current lifestyles, why we need a renewable energy source. So I'm going to take that as an assumption, and then talk about what we need, what type of renewable energy needs to make up our energy portfolio. No? I'll just keep going. So, so I stole a graph from Powering the Planet. Nate Lewis is Powering the Planet. And what he shows is the potential and the practical limits of all renewable energy sources today. And alongside of it, alongside of it, there's a bar graph showing how our use of 2009, our energy use, and our projected use. Thanks. And our projected use in 2030. And so what this shows is that by 2030, the only renewable energy source that can sufficiently supply our energy needs is solar. And so we have to have solar be a dominant energy supplier in our energy mix of the future. We really don't have much of a choice. So people have recognized this, and as a result, this is a very growing market and a very large market. It's $90 billion annually, and analysts predict it's going to grow 15 to 25% over the next year. And I don't mean to bring back bad memories of late problem sets, but this is a log linear graph. And what you can tell from this is it's roughly grown linear, this market, from 1955 to 2010. And so it's growing very rapidly and is already a very big market. So a lot of countries have recognized this. And in particular, China has done a very good job of putting incentives to attract manufacturing into their country to make use of this growing field. So these are some of the subsidies that they offer and some of the incentives. So for example, they provide low cost and quick unsecured loans for solar cell manufacturers. They also facilitate the construction of a factory and encourage you to build the factory to more capacity. They have lower taxes, so 15% versus 35% if you're in a high-tech field. They also have lower material costs and lower equipment costs. So if you're building a factory in Asia, you can buy equipment that does roughly the same thing but has lower cost. They also have lower overhead and lower labor costs as well. So all these make it very compelling to manufacture in China. And the market has responded to that. And so this is a graph. So as you can see that the market has grown significantly in the US up to 2010. This graph only goes to 2010. But in China, it really has exploded. And so they've really done a good job of attracting manufacturing in the solar cell market to their country. In the US, the story is a little bit different. Unfortunately, renewable energy and global climate change in general has become a partisan issue in the US. And partly as a result to that, we tend to fund, well, we fund all energy sources, but we tend to fund renewables at a very small percentage of the subsidy pie or the incentive pie. So there is a lot of controversy and debate about how much incentives there are. But what I find interesting is these are two different studies. And although they don't agree exactly, the overall conclusion is very clear. Renewable energies has a very small piece of the percentage of the incentives that are going into fund energy. So if you look on the right, the renewable energies are 5% of the subsidies. And on the left, if you just look at the solar piece, it's roughly 2%. So I think given that solar and renewables in general have to become a big market, and because they're not a mature market, to me it seems like we should be funding it a little bit more to encourage that to happen more in the US. So there's a lot of very smart people in DOE. A lot of them are MIT alum. And so they've figured out that they have a limited source of resources. And they also know that funding manufacturing improvements is very expensive. And therefore, incremental improvements are very expensive. And furthermore, traditionally, we think of private equity, private risk capital, helping fund more incremental developments. But this is not true right now in solar. The American VC community it's a tough environment to raise private risk capital in the US for renewable energy right now. And also the capital model for doing manufacturing doesn't fit very well with the VC traditional model that was used for IT. So, but assuming that private equity usually funds incremental technology and the pie is limited, our friends at DOE have made a very rational decision that they tend, in general, to fund higher risk, higher reward technologies. So I recognize this is a generalization and isn't true of everything they funded, but there is a trend towards that. In solar, though, the dominant technology, which is crystalline, the incumbent, has done an amazing job of incremental improvements. So these incremental improvements added together have had an amazing effect on decreasing the cost of solar energy. So this is a graph of price per watt, which is how you measure the price of a solar panel. And it shows the graph starts from 2009 and goes to today. And we're currently at about 85 cents a watt. And back in 1985, we were at $7 a watt. So that's an amazing drop. And again, this is all from the incumbent. There's no new material. It's just crystalline silicon technology. So because of this price drop, it remains to be the dominant player. So it's 85% of the market share. So the story in solar is pretty consistent, and I picked 4 examples here. I don't have time to go through all 4, but what happens is, in general, it's invented in the US, and maybe some manufacturing happens in the US, but then it often moves to Asia. So take, for example, SunPower. They were invented by Dick Swanson, founded by Dick Swanson, a Stanford professor. And they built their first factory in California, and now they have 500 megawatts in Asia. So most of it is in Asia. And just recently, they were acquired by Total. So this is a consistent story. So in conclusion, it's become more of a partisan issue than I would like, but I have to argue that grandchildren are not partisan, and we should consider this issue more seriously. And this has led to reduced funding in the US to help PV companies, and at the same time, private risk capital has shifted its focus away from clean tech. And meanwhile, China has very good incentives for solar manufacturing, and so they have a very good manufacturing base in China. So as a result of this, most of cell manufacturing has left the US. There are still a few exceptions. And what scares me the most is we think of ourselves as an innovation economy and the most innovative country in the world. But without manufacturing, what it means is that innovation will be on remote control, and it will be slower and less efficient. And it also is subject to the preemption of local developed expertise. So that makes me the most nervous. So this is sad for the US, but it's also unfortunate for the solar community. Because I feel like the US has a lot to offer. We're very good at entrepreneurship, and we're very good at being creative, and we have the best education in the world, and we have very good resources for risk capital as well. So it's a shame for the PV community as well. So my dilemma is, as a US citizen, I'd very much like to do manufacturing in the US, but as you can tell, the evidence, the incentives push a business owner and a board member to do what's right for the company, which isn't always that. So that's my dilemma, and I hope with the combined intellect in the room, we could maybe facilitate a discussion that leads to the answer. Thank you.
I'm going to do AV for a second here, just because it's my laptop, and I'm right here. Okay, there we go. So, Marcy, thank you. So next up, our last speaker, another alum entrepreneur. I'll introduce Nate Ball. Nate is the CTO and co-founder of Atlas Devices, as well as a host on the PBS Kids show, The Design Squad. Today, Nate is going to tell us about how he manufactures advanced hardware in a bootstrapped startup. Nate?
Thank you. How are we doing for sound? There we go. Well, I'm glad to get to be here today. I don't often spend a lot of time actively thinking about how it is that we manufacture things at Atlas Devices in the grander scheme of things, especially for advanced manufacturing. Although I also didn't expect one day to be hanging from a helicopter, climbing into it on a system that I got to develop with friends here at MIT while a student. As I've learned, the MIT experience is full of hard work that leads to exciting surprises, and so that seems to continue. We build a number of different products at Atlas Devices. We're still a small company. We're about 10 people. We're based over in Sullivan Square, so it's still very close. Our main product that we build, that we've gotten the most notoriety for so far, is the Power Descender. And rather than try to explain to you how this thing works, I'm going to show a 2-minute video that talks a bit about it. We got featured on History Channel's show Modern Marvels last fall. So here's a clip from that. Oops.
Scaling a mountain has become the metaphor for taking on a nearly impossible task. The slow, difficult climb to an almost unforeseeable end. Now, imagine a device that replaces the human effort completely, allowing you to literally dance up a rock surface. Atlas Devices has built a machine enabling you to do just that. No bigger than a large shoebox, the Power Ascender is a reverse propeller, capable of hauling over 20 times its own weight.
The easiest description for it is actually that it's kind of like Batman's tool belt. It's literally the part that pulls you up the rope. We've got a big battery here, motor in your gearbox, and an electronic control unit that controls the speed. So I can just clip with any standard carabiner, and I'm ready to climb. So once it's threaded, I can adjust the speed. I can climb very, very slowly, and then when I descend, it releases the brake. If I let go, hands-free anytime, I'm going to stay there in place. But if I want to go up, I just adjust that variable speed trigger and can go slow, or I can move pretty quick.
In 2004, a group of MIT students who later started Atlas Devices were enlisted by the Army to build a new climbing instrument for tactical missions.
Breezy, get up here with this one right here.
They were in need of a device that would allow for quick ascents across the mountainous regions of Afghanistan. In addition to helping troops in the field, the Office of Naval Research also foresees potential in the Ascender for maritime and rescue operations. By threading rope through a litter and the harness of the rescuer, the device can pull the weight of 2 people out of a compromising area.
So in other words, that could become a one-man rescue operation where now we would have to use 2 or 3 people in the same situation. I can do the same thing from a helicopter.
Traditionally, heli rescue efforts require aircrafts with specialized winches to airlift endangered personnel. The Ascender has the potential to convert any helicopter into a rescue vehicle, with its ability to lift hundreds of pounds at once.
So, thank you. Thank you very much. We developed this while we were still students at MIT, and we actually founded the company in 2005, just after the design competition that the project came from. We got to be part of the soldier design competition at MIT, hosted by the Institute for Soldier Nanotechnologies. And what we get to do is get a little bit of funding to build real live functioning hardware that supports soldiers in the field. Now, MIT engineers students actually get to compete against West Point cadets from the US Military Academy, trying to build equipment that supports the soldiers. So after we made the first prototype, we got to test it right here in their Z Center over the pool for safety. We recognized that this capability was really powerful and that we should really do the best we could to try to take it to market and try to especially support the people that asked for that capability in the first place, which was the soldiers that were out there in the field. And while we were here at MIT, we had lots and lots of resources, many of which I didn't appreciate at the time until after we had left. But starting the company, it was in 2005. I was a senior at the time. Most of my colleagues were either seniors or grad students. I still had a master's degree to do. So for the first 2 years, between 2005 and 2007, we were working in the lab by day doing graduate student research. And then at nighttime, we were working on the Atlas project. And here at MIT, we had equipment to support prototyping, both in the lab where we worked as grad students, and in fact, all around campus. There were all sorts of machine shops and things available for us to try to use. There were also experts in technology, as well as materials and sort of everything we needed to figure out how to make a system that had never really been built before, especially with the kind of mechanical power output that our system has while being so small. We had business help. We were just engineers. We didn't know what to do to start a business. So over our entire history, we've been mentored by people at the Venture Mentoring Service who have really helped with our business development, figuring out how to find, serve, and support our customers as we grew. And then, of course, there's just the sheer technology we get exposed to here at MIT. Early on, we got help from Professor Chang in the Materials Science Department, of course, with his high-power, high-energy batteries. And that's been a trend that we've gotten to continue to make use of, is our close ties to the people that are generating this high-tech equipment here at MIT. Every time something new comes out, we get to incorporate it into our system. And that just means enhanced capabilities for our customers and more solidification of this new capability, which I'll tell you more about in a second. Of course, when we left MIT, after we were finished being grad students, we couldn't build things in our lab anymore, so we moved the closest place that we had access to set up a little office, which was the basement of a former fraternity building on Beacon Street. Now, a number of things characterized that workspace. Manufacturing capability is not one of them. Some people would describe it as elbow-to-elbow quarters. I like to think of it as sitting within high-five distance of your colleague. But we spent 2.5 years in that basement. And we got a lot done from there. We chose to bootstrap our company, which really constricted the actual resources we had. We had no money to buy a machine tool to bring in there or the space to even put it in. And so we really struggled to find the resources we needed to innovate on our mechanical system, as well as begin to produce it once there was demand and once we started getting orders. The other thing is, without a conference room, we had no good place to bring high-profile customers. So when we got to host a Navy admiral there, the usual line was that we were under construction, which really happened a lot. He said, yes, Admiral, we'd love to meet with you. Unfortunately, we're under construction, so could we just meet at Starbucks nearby? And so in almost every way, we got used to working with what we had. But our real struggle was, how do we continue to innovate on this system? What we had coming out of school was a functional prototype, and yet we got our first military order right around the same time. And the best we could do was rent nearby shops for us to build the project with. But after we moved away from campus, it was no longer appropriate to rent our former professor's personal machine tools to use. And so we needed a partner to work with. And we especially needed a partner that was as flexible as we needed. We kept changing the design every time, as you do when you're an engineer. You can always think of something better. So every time we got a new order, we're putting new R&D into that build, which means even if we had the resources to scale up our manufacturing, it wouldn't have necessarily been the best path, because the technology we developed, we still didn't know all of the exact specs for how to make it work the best for the customer. The customer, this new capability of powered climbing, was such a new capability to our customers that they didn't know all of the aspects, all the functionality that it needed to provide. So with such fast R&D happening, we needed a really flexible supplier, and that took us a while to find. But now, oop, there it went again. I'm going to try running it from here. All right, well, we did find that supplier, and we also had to do a lot of customer development to find the right customers as well. This technology has many applications all over the place, not just in the military, but for all sorts of vertical climbing tasks. MIT was, in fact, one of our first customers. You're all familiar with the beautiful scoreboard that's cantilevered out over the pool in the Z Center? That's very hard to get to, so every time a panel goes out, they have to rappel from above. So we built them a 2-axis system, so they tie one rope to each corner, they come down to a center point that you hang from, and the system can drive left, right, and up and down. So that was our first industrial access application. Similarly, wind turbines have a lot of trouble getting serviced. It takes a long time for the operators that do the even oil changes in the gearboxes to climb up and down, so our system can be used there as well. But especially focusing on the military market, because we started there, we wanted to serve them. And additionally, they're a fun customer in that they really push the technology. We are highly incentivized to max out every material property of the system that we put into it. Because if you're not familiar with what the soldiers have to carry when they're fighting, the average fighting load of a soldier is around 75 pounds. That's when you're out there in the desert heat, running around, trying to do your thing. You've got all this weight on top of you. So even if we're offering them a very powerful new capability, it really can't add a significant weight to what they're already carrying, no matter how powerful that capability is. So we are highly incentivized to make it as lightweight as possible, while still being able to make it perform and lift the loads that we need to. We've been able to do that, and so I'm proud to say we're no longer in the basement as of 2009. We now have a larger facility in Sullivan Square. We now get to support all 4 branches of the military with our products, as well as a few other government agencies. We've also begun exporting. Actually, a fun recent piece of news this week, we were proud to receive an award. We were the Massachusetts Exporter of the Year for the SBA. And thank you. Thank you. We feel especially good about that. We faced some other challenges for export, namely that we do fall on the U.S. munitions list. We've been heavily supported by the military for development, so we can't just export anywhere. We have a lot of extra paperwork to go through. So we're proud to be able to support other friendly countries through those appropriate means. And we also have an expanding portfolio of high-performance R&D products. As we have developed ourselves as a company, we found the right kind of supplier, which was a very fast, flexible supplier. In fact, just to give you a bit more detail about that means to us, our key supplier that manufactures, or that does all the machining work, we still assemble at Atlas Devices in our house. We have a machinist that's very nearby in Woburn as well. And what characterizes them is they're about the same size. So when we have a big build, they dedicate their entire company to our project. But the big thing is, it's run by mechanical engineers. They're not just machinists, they're engineers themselves. And so they're such a close partner to our company, they actually understand exactly what we need to do to iterate super fast. And so not only do we have them do our production of the machine parts, but we have them help us prototype as well, so that once we have a new design hashed out, it's the same people that are manufacturing it. And that way, we never have to be tied down to a given process that could sacrifice capability when our customer requires something different and we have to go in a different direction. Similarly, we found our niche with our customers, and supporting the special operations community has been one of the real key things we've moved into as a company. And there's a number of reasons why they're kind of an ideal customer for our capability. Coming out of MIT and building up these resources as a group to react very, very quickly and generate a brand new prototype of a new technology within a week is our goal. From zero to alpha prototype within a single week is our goal with the company. We're not quite there yet. We still take a couple of weeks to do that. What it enables is for our customers to come to us and request a new capability, and we can move on it faster than anybody else out there. And that's due to the skills we picked up here at MIT, as well as those key suppliers. So between the suppliers and the ideal customer, we've created a very fast feedback loop for rapid technology development that really serves our innovative goals, as well as our goals as a company, which is to create revolutionary products, especially mechanical products. That's our sweet spot. Over time, we've picked up a few pretty key understandings, and these begin to play into the advanced manufacturing notions that we've been talking about today. One, to support our customers' needs, the conventionally available materials often don't suffice. So it's not always that we're going straight to composites. That's often where the mind goes when they're thinking about advanced materials. We're also using all sorts of other alloys, advances in different plastics and things, and even in our ropes is a great example. Normally when you're hanging from a system that includes ropes, if you're rappelling and stuff, what you need is an ultimate tensile strength of every component in the system to be at least 5,000 pounds or bigger. You want a safety factor of about 10 to 1 when your life is on the line hanging high up in the air. So our system itself, the ascender, has to be strong to over 5,000 pounds. With a safety factor of 10 to 1, that gives you about a 500-pound safe operating load. All of a sudden, our customers wanted to lift 2 people at the same time for a rescue situation. That adds up to more than 500 pounds. In fact, their requested number was that our systems lift 600 pounds. The normal ropes that you can get can't do that. But yet, recent advances in polymers and things have given us ropes with extremely high tensile strength. They're using these long UHMW fibers that line up over long distances, and what they give us are ropes that can handle that. And so, all of a sudden, with a rope with a tensile strength of 20,000 pounds, it really expands the capability of a product that we can build. Similarly, to successfully manufacture these tightly integrated designs, where every single part of our system has to do 4 or 5 different things at the same time, our suppliers have to be really not only flexible, but creative as well. We're often solving problems in parallel and alongside our suppliers so that they can help us build what we need to be built, which in most cases hasn't been done that way before. The other thing that we've learned is our customer doesn't just want to buy a gadget, our customer being especially the military. what they need is to assimilate a new capability. And that means a lot more than just giving them an ascender and saying, on your way, here's how to use it. We have to provide training, and we have to create training that's relevant so that they can incorporate the new capability into their, what they call TTPs, or tactics, techniques, and procedures. Additionally, we have to figure out how to service the units over 5 to 10 years. And these are normal things that a company has to do when they're supplying products, but it was a new thing for us to think about it as a single capability that we were selling and providing. And so that plays into the bundling idea in the next slide. So here's that slide again, thanks to Professor Weck. And tying things all together, we don't do the material design ourselves, but we very frequently exploit enhanced material capabilities that are coming out from innovations in the lab. We've done that with our battery technology. We've done that with heat transfer. Of course, tensile strength and how strong things are for the ropes and the mechanical system as well. And then a bit about the continuous manufacturing for fabrication and assembly. What we've chosen to do, because our suppliers have relatively advanced machining capability, they can do many axes of machining. So that means we can easily machine on one side of a part, flip it to the side, machine a whole lot more, flip it to the other side. This is all automated, and then machine on that, all 6 sides very easily and quickly. Because they're so creative in how they can machine parts, that means we can group complexity of our system into a single part and have the automated machining capability take care of that hands-free. So whereas to build a complicated system, we might used to have had to make many, many simple parts and then have people assemble them together. This way we can group all that complexity into a part that's automated in how it's made, and that speeds things up even further. And the last part is that bundling idea again, when we're providing an entire capability rather than just a gadget. And so even though I don't walk into Atlas every day saying, it's a fine day for advanced manufacturing, as I look at this slide and consider the things that we use every single day in order to build and supply our products, we absolutely are using advanced manufacturing techniques, and that's a big reason we're being successful as we are right now. And the thing I want to leave you with is this idea of force multiplication. It's a term the military uses to describe when a new technology allows one soldier to do the job of several. Force multiplication. And that's kind of the thing that we get with advanced manufacturing. We can do very, very much, both R&D and production, as a very small company of 10, because these advanced manufacturing techniques allow our forces to be multiplied. So that's a bit about advanced manufacturing at Atlas, and thank you very much.
Okay, Nate, thank you very much. So I'm going to ask that our speakers join me on stage. I've been advised that we can keep you here until 1 o'clock, running about 15 minutes over. I see a number of questions on cards, and we'll try to ask as many as possible. So, speakers, please. So we have initials here. Is that us? Okay. No, those are not, that's not us. Do I have the cards? Oh, they're going to read them. Okay, they're going to read some of them first and get the real good ones. Perfect. Well, we're sorting through some questions. I'll start with one. So we've seen, I think, a pretty good spectrum of the rapidly changing world of manufacturing, and not only in terms of technologies, but where and the types of products. I wonder if each of you could comment a little bit on sort of the importance of the ecosystem in which you work, in terms of how important is it to have proximity to partners to potentially pursue the endeavor. Nate, I think you touched on it first. Let me work this way.
Yeah. Proximity to partners has been huge for us. We've really actively sought out suppliers that are nearby to help us out. And our incentives to do that are several-fold. For one, actually, Ollie alluded to it in his talk. Because we manufacture a military product, we're somewhat restricted in the suppliers we can use. We can't use people from China. But the other thing is that we notice a huge difference in suppliers even just a couple states away. Managing one of our key suppliers that makes a subsystem for our unit, they're not in Massachusetts, and the effort it goes to for us to communicate with them and work really smoothly in parallel in the way that we need to develop a new capability for the technology, the effort is exponentially higher the further away we go. And so once we found our supplier in Woburn, where I can hop in the car and drive over there in about 20 minutes, you could just feel the design cycle from innovation to manufacturing speed up. So that really keeps us close.
It's a good question, because I think being on the East Coast and being by Massachusetts, by MIT and in Massachusetts has really helped BandGap a lot. So it's not just recruiting, but it's having access to the mentoring service and having consultants that are professors at MIT. We have Professor Dalamo and Professor Dresselhaus on our advisory board. And also having a community of entrepreneurs to ask questions to has really been helpful. So not just suppliers and customers, but also a community of people to recruit from and to ask questions to has been very helpful.
I'll give an academic response. I think is it on now? Is it on now? I think my blouse design is not working very well. From an academic perspective, where we really are focused more on the R&D part of it, it really is about the challenges that exist for interdisciplinary research. And I think this actually was alluded to earlier in the remarks about Susan's presidency, that really the convergence of life sciences and engineering and how that's felt in so many different facets of what happens here for us at MIT. If I look at the kinds of things that we're doing, where my lab is primarily composed almost exclusively of chemical engineers. We've started to get more microbiologists involved, but the work that we do has a very strong biological component. And so there are many times where I sit down with a student and say, okay, who do we know that can answer this question? And so we have thesis committees that are composed of biology faculty to help us think about the microbiology. And we put chemistry faculty on our thesis committees to help us think about structure-function relationships for chemical molecules, as well as some of the aspects that come into separations and other materials properties. And so certainly the rich environment that we have here at MIT of universal excellence, of not having one department that's the shining diamond in the midst of you know, a bunch of I don't know, what's the non-diamond, the anti-diamonds. What we have is a community where, because the excellence is universal and widespread, that we really can pursue new research areas that cause us to go beyond traditional disciplinary silos. And I think our students really benefit from that as well. That's where they actually have the most fun, is in learning across the traditional disciplinary boundaries.
Very quick, I think it's not a black and white issue. There is a lot of value to proximity, and Susan mentioned the cranes, you know, the cranes, the ecosystem that is existing and that is expanding around MIT and other research universities. There's a reason why these companies are making billion-dollar investments to be close to the universities, to have that interdisciplinary, these close feedback loops. But at the same time, there's been exciting developments, largely enabled through the internet, that allow you to exchange CAD files, to exchange manufacturing instructions, to really use the whole world as a sourcing potential for sourcing. Depending, you have some restrictions, Nate, that you mentioned, but for example, a very exciting portal is MFG. You mentioned government, manufacturing.gov. I encourage you to go visit mfg.com, manufacturing.com. It's amazing. Hundreds of millions of dollars of parts and manufacturing activities are now being brokered and traded through the internet. So the real challenge for manufacturers, in my mind, is to find the right balance, to understand what is your core competence, what are the key components, the key enabling technologies in your product that you need to master, that you need to have control over, that you're going to innovate at in your cluster, and what are the things where you should leverage the internet, you should leverage the global capabilities that we have. So it's very much a hybrid approach that I think will be, is the wave of the future.
Yeah, I think for the research we do in using computation, for us, proximity to labs is really critical for the students who work on the research projects, echoing with what Kristala said. with our collaboration in computational modeling and experiment, we really benefit from the local area here, and that our students who work on the computers can actually go to the labs and see how these materials are made, and the other way around. So I think proximity and communication across disciplines and being able to actually drive there and talk to them in person, I think, is really important in that. I mean, the internet has done a lot of useful things, and I think it's great to work through email. But in my experience in research, when you actually sit down and have a conversation and you have discussions, especially among the students, it's terrific.
Yeah, just a quick note to tie into that. We actually did used to use mfg.com to find new suppliers domestically. You can literally check every country you want your request for quote to go to, and it sends it all out, and then you suddenly get parts, quotes coming back. So that worked for us for a little while when we had no other resources, but it helped us find ones that were close by. And to your point, as soon as we could sit down and have a discussion, we found that's more the interaction we needed, but they were both useful.
Thank you. So I'm going to take some questions from the audience now. This was originally directed at Ollie, but I'll actually expose it to everybody. But what actions and policies should the United States government pursue to enhance U.S. manufacturing, particularly in the context of an upcoming election, but just in broadly otherwise?
So I'll just bring up one point which we haven't talked about yet today, and that's tax policies. The tax, it's very interesting when you talk to a lot of the smaller and the larger companies. The large companies have an army of tax lawyers that help them optimize, in a sense, their tax, how much taxes they owe. One of the big challenges, and this is kind of different in the U.S., is that U.S. companies are being taxed on their foreign revenues unless those if those revenues are repatriated to the United States at a nominal tax rate of 35%. Now, if those revenues are not repatriated to the United States, for example, to be reinvested in R&D or manufacturing plants, you can defer those tax payments. And it's really a very, very counterproductive policy, which encourages, in fact, not to reinvest those foreign earnings in the country. And that's something that at the highest level, I think in Washington, it's one of the top issues that has a dampening effect, I think, on manufacturing in this country that needs to be addressed. There's others, but that's very high on the list. And I believe AMP will address that in quite some detail.
So one of our most abundant feedstock sources is our trash stream. What are the challenges and opportunities to better use, or does re-engineering prohibit that? Opportunities for bioconversion, burn it for electricity, bury it? What's your perspective?
So I'll give the beginnings of a comment on that. There actually is quite a lot of research worldwide on how do you account for waste. And the slide that I showed, which was looking at distribution of biomass in the U.S., one of the 4 categories included in those calculations was municipal waste streams. So I'll start by saying then that this is certainly an issue in terms of reuse that is on the forefront of a lot of people's minds and activities and efforts. One of the primary challenges, and this is true for most any type of chemical processing that you can think about, is the heterogeneity of those waste streams. So the challenge that you have in dealing with waste in whatever form it comes from is that it's inconsistent. And so we tend to design processes that are based on knowing what the inputs are. And in order to then design a process where those inputs change, and change in many cases in unpredictable ways, it requires a new way of thinking about the process and a new way to actually implement process controls, as well as an ability to restart the process in order to make this work. I think there's certainly the potential to have that operate successfully. One of the nice examples are municipal wastewater treatment facilities, many of which rely on biological systems, on microbial consortia, to convert wastewater into a non-toxic stream. And there has been an effort within, this is mostly work done in an environmental engineering context, to actually understand how different variabilities or variations in the input affect what happens on the output. But there is this continuing phenomenon known as a process upset, where the thing just stops working, and you have to figure out how to restart it. And the challenge, of course, now, if you're thinking about this from a treatment facility perspective, then you can typically build in the buffers to be able to handle that. If you want to make a product, and you have to worry about now that you may get a feed stream that causes the whole thing to be shut down and have to be restarted, and there are certainly some additional challenges associated with that. So we are, as a community, I should say, aware that the feedstock exists. There certainly is a lot of effort being put into trying to figure out the best way to use that as a feedstock, especially the most carbon-rich components of it. But there are some very significant challenges when we think about it in a manufacturing context.
So this one ties together a number of things we talked about, a number of speakers. So here it goes. In the context of the National Network for Manufacturing Innovation, the first Innovation Manufacturing Institute is in additive manufacturing. So for Nate, would 3D printing help in manufacturing parts that could potentially save in weight and cost, and what do you see as the avenue for that? And additionally, would synthetic spider webs or silk materials work better for higher strength cables?
To the second question, yes. And for 3D printing, yeah, it can absolutely make a big difference. Recently, 3D printers have become really affordable. We just picked one up that we're leasing for about $300 a month. And having that capability in-house is tremendous. It takes away all the barriers to entry for trying out a physical design. So for R&D, it speeds things up hugely. We're even beginning to print a few production parts. Pretty much everything on the outside of our system has to be metal. So as a company, we can't afford the ones that print in titanium yet. But that will undoubtedly come down as well. And the cheaper and more viable the materials become that are being 3D printed, the more likely we'll be to use them. It's kind of the ultimate for flexible design. You literally just hit print and you get parts out. It's beautiful. So we'd love to manufacture everything that way if we could manage it.
So this is a question for Marcy, I think particularly. Shale gas, oil fracking will lower costs and change the geographical distribution of petrochemical products. So will this lower the cost, set back development of alternatives?
Sorry, it will lower the cost?
Lower the costs and then lower the cost on other fuel sources so that it sets back the development on photovoltaics, on moving forward on the routes that we're pursuing now for alternative energy.
Right. So the right way to think of shale gas is this is a great opportunity for us to use it to levelize solar energy. Because one of the issues with renewables, and actually most renewables, is that you can't always predict how much power you're going to get out. So for solar, if a cloud goes overhead, the power will drop. So one way to balance that is with batteries. Another way to balance it is with oil and gas. And so I see this as an opportunity that we really should take hold of instead of thinking, oh great, we have another 30 years of cheap fuel. I think we should use it as a way of saying, great, this is a way that we can extend our use of this valuable resource of oil and allow us to use more solar in the meantime.
So this is connecting some of the big questions in manufacturing, the big questions in energy and in simulation and modeling. So when you look at the complete life cycle, product life cycle, and incorporating sort of the recycling needs and biodegradability and where the products end up, is there an opportunity for modeling and simulating that?
I think so, yeah. Modeling simulation allows us to explore conditions and potentially timescales and processes that we haven't really tested in the lab. So if we were interested in making materials and products that we can break down with certain chemicals and certain conditions, we could design those potentially for this purpose. So just like we've designed for strength and toughness with these fibers, which could find applications in your devices, for example, we could also design using computational simulation for sort of breakdown, right? In fact, one of our projects deals with making the materials switchable such that they're normally very tough, but if you like, you can make them very fragile. You turn on the signal. So we work on the materials like this, and I think sort of in an airplane, you might imagine, or in a car, if a part is no longer to be used or actually dangerous for operation, you could just get rid of that by sort of targeting its becoming fragile, being dismissed. So I think, yes, this is a great opportunity in actually extending sort of beyond synthesis and actually thinking about how the material cycles back into breaking it down into the building blocks again.
So I think this will be the last question. This will be the last question. In the context of thinking about manufacturing in the context of people and technology, how can community colleges, in partnership or by themselves, serve as a place for educating and training a workforce in manufacturing when they have little or no established facilities?
I'll try that. I briefly alluded to it, but one of our modules in PI is looking at, this is a study led by Paul Osterman at the Sloan School of Management. He was really an expert in the community college system. It's been a real eye-opener, I think, for us, the other members of the commission, to see how important the whole community college system really is in the United States. We have roughly about 7-8 million students. We had our graduation yesterday here at MIT. Nationwide, we graduate about 2 million bachelor's students per year, so that's a population of 7 to 8 in the 4-year colleges. But we have a population that's about the same size in the community college system. Some of them are going for the 2 years associate's degrees. Some of them are using it as a transition into the 4-year colleges. It's a very important system, and as we're scanning and understanding how well the community colleges are doing across the nation, we're seeing a big variation. So we're seeing examples of community colleges that are really struggling to be meeting the needs, and we're seeing outstanding examples. And some of we have very good examples here in Massachusetts, North Carolina, for example, Ohio. There's a number of states where community colleges are very innovative in terms of how they connect with their local communities, their local ecosystems, leveraging facilities at some of the companies, providing both the fundamentals but also the applied skills that are really needed by industry. And this is, I think, probably going to be one of our top recommendations from PI, is to really strengthen that system and find ways in which we can have continuous training and education from the very advanced things we do at MIT and at our peer universities all the way down the line through including the community colleges. So this is one of the big points of leverage in the system, no question.
I think when I add to this, as I mentioned towards the end of my presentation, I think the MITx or edX initiatives, I think, tie in very nicely because they make facilities and educational initiatives or teaching styles and potentially facilities with virtual access available to many, including those at community colleges.
So with that, we're reaching the close. I just want to thank you for your attention. Hopefully we've adjusted a little bit your perception of what advanced manufacturing is all about, and maybe you'll recommend some of your friends and family to go into it. So I'd like to thank you. And our speakers once again. Okay. And then my last announcement is the Tech Day lunch is in the Johnson Athletic Center. The class of 1962 and spouses, please gather in the lobby to proceed to the Tech Day lunch together. So thank you.